Well, good afternoon. It's 12:30 or 2:32 on Monday, the 12th of October, 2020. This is supposed to be differential equations class, but right now I'm the only one here. I think Kira, I think is trying to come in. Let me see if I can admit her. There she is. So Kira is here. Okay. All right. So Kira, I was just getting started. I checked again to make sure I had posted Zoom correctly, and I had, so good to see that you showed up. Any questions, issues, problems, concerns before we get started? I'm already recording, by the way. Okay. All right, now where we were last time, I'm going to move you a little bit out of the way here. We had just started, we're in Chapter 2, First Order Differential Equations. We had just started Section 2.5, Solutions by Substitution. And as the foreword indicated, not everything's going to work by separation of variables, linear equations, or exact equations, but sometimes we can make some substitutions somewhat similarly like we did with those to get it into a form that we can do. Okay, get it into one of the other forms. So we're going to look at some of the possibilities there. We covered this first paragraph last time. Often the first step in solving a differential equation consists of transforming it into another differential equation by means of a substitution, and then maybe that new equation we will be able to solve using one of our other techniques or maybe some new techniques. Okay, now, here comes somebody, but I can't see who. I believe it's James, but I can't tell for sure. I think I'm going to have to go down to the bottom and open it that way. Yes, it is James, and I'll admit him. Okay, number 1 and number 3 are here. We're still missing 2, 4, and 5. Hopefully they will be getting here soon. Okay, so I think what I'll do is go back to minimize. Okay, James, we're on Chapter 2, First Order Differential Equations, Section 2.5, Solutions by Substitutions. And we had just started this last time. I'm doing a little bit of review of it right now. Did you have any questions, issues, or concerns before we get going on this?
No, sir.
Okay. So here's what we're talking about. So what if we can make a substitution? Here's typically how we do it. If we write the first order differential equation in what they call standard form, I believe it is, the dy dx, that's the only derivative you have, is some function of x and y on the right hand side. Now, one of the substitutions typical to make is instead of y, you put in some g of x and u, introducing a new variable u, and this variable u is also regarded as a function of x. Okay, so it almost looks to me like, okay, y is supposed to be independent of x, but it makes it seem like you're doing something that now is dependent on x, but in a roundabout way. But let's ignore that for the moment. If g possesses first partial derivatives, that new function g, that y is equal to g of x, then by the chain rule, the dy dx, okay, which if that were, and this is your independent variable here, I'm sorry, y is not supposed to be dependent on x. Is supposed to be dependent on x, because this is not a partial differential equation, this is an ordinary differential equation. So dy dx is some function of x and y, and we're going to assume that y then is a function of x because it's the dependent variable, but it's through this function g, which is g of x and u of x. Okay. g is a function of x and u, so g is a function of x, and then g is a function also of u, which is also a function of x. So if g possesses first partial derivatives, then this dy dx that we had here is equal to the partial of f with respect to x. Well, I'm sorry. Okay, they're doing it sort of backwards here. So let's write this as okay, right here. Dy dx here, not over here, but dy dx here is the partial of g with respect to x times dx dx, which we know is 1, plus the partial of g with respect to u, and then it's multiplied by du dx, and we said it is a function of the variable x. Now, this in partial notation, which you may not have gotten to yet, I know you haven't in Cal 3, I don't think you've hit it otherwise, is written as g sub x. That's a partial derivative of g with respect to x of xu plus g sub u, that's this term here, times du dx. Now this is an ordinary derivative. These are partial derivatives. If we replace the dy dx on this side with the dy dx over here, then that differential equation that we started with here becomes this one. This thing here is equal to f of x comma g of xu, which when solve for du dx, okay, that's this very last term here, they go around their ears to get around to their nose here. They just say, let's solve for that and give it the form of capital F of xu. Now, if we can determine the solution u, which they introduced up here, is really a phi of x, so why didn't they call it phi of x to begin with? I don't know. I mean, this is the part that doesn't make sense. Of that last equation, then the solution of the original differential equation is y is equal to g of x comma phi of x, which is exactly what you have here, except you have, rather than u, which is a function of x, they have phi, which is a function of x. So if you want a phi, why didn't they make it a phi up here? I don't know. In the discussion that follows, we examine 3 different kinds of first order differential equations that are solvable by means of substitution. Okay? Now, all that was sort of blah, blah, blah. Now we're going to get to specifics. Okay? Now, the first of these is called homogeneous equations. Now, later we're going to call something else a homogeneous equation, or at least a homogeneous system of equations, or equation. And if for those of you in linear algebra, you know there's another homogeneous system of equations. That's where the system comes in. But these homogeneous equations have, and they give the definition here, which doesn't do a lot for me. Okay? And I'll tell you how I look at it. But let's first look at how they do. If a function f possesses this property, the f of txty is exactly t to the alpha of f of xy. Okay? For some real number alpha, then x is said to be a homogeneous function of degree alpha. Okay? That leaves a lot to be desired in mind. And here's an example, and this makes perfect sense here. F of xy is equal x cubed plus y cubed. This homogeneous function of degree 3, since if you let do f of tx ty, which is what it says to do here, you get tx cubed plus ty cubed. Factor out the t cubed, and you get t cubed times x cubed plus y2 cubed, and that's t cubed times f of xy. Okay, now that's one way of expressing it. Seems like a lot easier way to say, okay, now let's do this one. Whereas f of xy is equal to x cubed plus y cubed plus 1, not homogeneous, because this is a third order, that's third order, this is a zero order, not homogeneous. So another way to look at what they mean by a homogeneous equation is that every term in that equation has the same order. Okay, so a first order differential equation in differential form, m of xy dx plus n of xy dy equals 0, is said to be homogeneous if both the coefficients m of xy and n of xy are homogeneous functions of the same degree. So in other words, that is homogeneous if, and here they go to their definition again, m of t x ty is equal to t to the alpha m of xy plus, and n of t x ty is t to the alpha n of x y. Okay, now why introduce this concept of t? It's certainly correct, it's absolutely correct, but it seems like a much easier way to express that. In addition, if m and n are homogeneous functions of degree alpha, we can also write m of xy is equal to x to the alpha m1 of u, and n of xy is equal to x to the alpha n1 of u, 1u, where u is x over y. Okay, now that is leading to something we are actually going to deal with. And m of xy is equal to y to the alpha mv1, and n of xy is equal to y to the alpha in v2, where v is x over y. Now, they now say, see problem 31 in the exercises. We're not there yet. We'll get there, okay? Properties 2 and 3 suggest, this property and this property, suggest substitutions that can be made to solve a homogeneous differential equation. Specifically, either the substitution y is equal to ux or x is equal to vy, where u and v are new independent variables, will reduce the homogeneous equation to a separable first order differential equation, and as such pretty easy generally to solve. Okay, now to show this, observe that a consequence of 2, let's go back up here and see 2, that's this one right here, this one right here. Okay, a homogeneous equation, this can be written as alpha x to the alpha m of 1u dx plus x to the alpha n of 1u dy equals 0, or m of 1u dx plus n of 1u dy equals 0, where u is x over y, y is u times x. By substituting the differential dy is equal to u dx plus x du into that equation here, or here, either one of them, but no, this one, when you divide it out to x to the alpha, okay, you get this form. Now, m of 1u dx, that's the only dx part, plus, yuck, n, I'm going to have to scoot down a little bit. I keep dragging that other thing up here, the toolbar, okay, inadvertently. Okay, so you're plugging this in for your y is equal to ux, okay? So dy is equal to u dx plus x du, and insert that in here. Oh, here's Miguel or Jesus. I can't let him in that way, so I'm going to have to come down here and let him in this way. And there he is, coming in now, I hope. Yeah, joining the class now. So we got 1, 3, and 5. The odd students are here. Not that y'all are odd or anything. The even students, Ryan and Jemanuel, not here yet. Okay, hopefully they'll be getting here. So let's minimize this one. And what we're doing is substituting this differential, the dy, right there, this thing right here, in for that, and gathering terms. Okay, it feels like here I probably should do this on the whiteboard. Let me do that. Okay. Because they are skipping enough steps, it makes it really hard to see. Okay, now what I've got to do here is move James over here just a tad and move this toolbar up here above him. Okay, and then adjust my whiteboard slightly so I do have maximum white space. Now I do have a problem in that box is in the way, but I'll try to work around it. Now I thought I heard my phone ring downstairs. Yeah, I'm sorry, I'm going to have to take a break here because I think we're supposed to have a hook, and my wife's at work at the office today, so she is not here to check on. She usually doesn't anyway, but anyway, sorry about that. Let me find what I did with my thing. Now, where were we? Okay. Okay. Okay, I have lost my place here. Oh, I'm sorry, I'm on the wrong page. No wonder I can't find it. Okay, here is where we were. Okay, I'll have to move this to my lap. Sorry about the confusion, folks. Was anyone trying to get in while I was gone? Let me check that first, because I had to go downstairs real quickly. I don't think so. I think we got the same 3 we had when I left. Okay. Now, all right, let me see if I can pick up where they kind of left you hanging. Here you have m, which is now a function of 1 and u times dx plus n, which is now a function of 1 and u dy is equal to 0. Okay. Now this u is equal to y over x, which implies, of course, that y is equal to ux. Now don't get this confused with our mu from earlier, even though they look somewhat similar. Okay, taking this equation, we do a dy is equal to u dx, taking a exact differential of it, u dx plus x du. Okay. Now, we're going to substitute this in for this dy here. And this is where they just skipped all sorts of steps. M of 1 u dx, that hangs by itself okay, plus n of 1u. Now, instead of dy, we're going to put this in here, times u dx plus x du. Okay, and that's equal to 0. Okay, let's get all our dx's together here. Here's a m of 1 u plus n of 1 u times u dx plus, that's this term and that term, plus n of 1 u times x du is equal to 0. Now, what we're going to do now is notice that everything in this parentheses is a function of u and u alone. This is a function of u and u alone, but this is a function of x and x alone. So basically, let's get the x's together, and that's basically a 1 over x dx is equal to, now we're going to change signs of things here, minus n of 1 comma u over m of 1 comma u plus n of 1 comma u times u. Okay? Now, this is a function of x alone here, and this is a function of u alone here. I didn't write my du in here. Should have. Okay. Now, this one is real easy to integrate. Log of x. Okay. This one's not so much. Okay. Now, they left on the same side. I moved it to the other side. At this point, we offer the same advice in the preceding sections. Do not memorize anything here, especially that last formula. Rather, work through the procedure each time. The proof that the substitutions also lead to separable equation follows in an analogous manner. If you use the other substitution, v is equal to x over y, and then x is equal to v y. That works the same way. So we're not going to use this anymore, but this was just to show you this does become separable. Okay, now at this point, let's do example 1. So let's clear the drawings here, and let me make sure nobody else, I don't think anyone else is coming in, just the 3 of you here still. Okay, here's example 1. X squared plus y squared dx plus x squared minus xy dy is equal to 0. Now, especially in this form, that looks like it could be an exact equation. So what we would have to do is do the partial of this with respect to y, and that would be 2y partial of this with respect to x would be 2x minus y. No, those are not equal. So no, that won't work. But here's the homogeneous part. Look at the degree of each term of both of your functions here. This is degree 2, that's degree 2, that's degree 2, and this is 1 plus 1 is 2. All those terms are the same degree, therefore this is a homogeneous differential equations. Okay, and since it is homogeneous, we can use the substitution that we were talking about. Now remember, they were one of two. Either y is equal to ux or x is equal to vy. Okay, now I can't just look at this and say which one looks like it might be the most promising. Hold on just a minute, this room's getting sort of warm, so let me turn on my ceiling fan. It's getting a little stuffy to boot, in addition to being warm. Okay, let's just take that first one and see what happens. Okay, and again, we're going to say dy is equal to u dx plus x du, and this would then be, let's just make sure they are doing the same way we are. Yeah. Let's do our substitution then. Okay, this will be x squared plus y squared dx plus x squared minus xy, and then instead of dy we write u dx plus x du. Now I sort of messed something up there too. I should have gone on and put this in. So let me do that now. Sorry about that. Whoops, using the wrong eraser here. Okay. Instead of y squared, we're going to put u squared x squared. Uh-oh. Now this time it is my phone. Hold on just a minute, folks. Good afternoon. Yes. Okay, I'll go let you in. I'm in class now, but let me pause the class back where we left off. Okay. Now, I was just, oh, I dropped my pen. I hope it didn't break. It fell in something soft, so hopefully it didn't. Okay. Okay. All right, let's get back to our drawing here. Okay. So here was, since y is equal to ux, this y squared becomes plus u squared x squared dx. This y becomes ux, so that would be x squared u, and then the dy becomes u dx plus x du. And for some reason I have a y there. I don't know why. Okay, so let me erase the y, and that's a u. Okay, sorry about that. And nobody caught me on that one. You're supposed to catch me and keep me from doing stuff like that. Okay, now let's gather the dx's together, and we'll deal with that. So this is now, I'm going to factor out an x squared times 1 plus u squared dx plus an x squared times 1 minus u dx. And now I'm going to move this to the other side, and this will equal, this will be an x squared times, over here it's going to be a u minus 1, because I'm moving it to the other side. That reverses the order there, times x, so that's going to make this an x cubed u minus 1 du. Okay, now yeah, no, this doesn't look differentiable to me. Have I done something wrong? So I've got x squared times okay, looks like something squirrely here. Let me see. X squared plus u squared, x squared dx, got that, plus x squared minus ux squared, got that, times u du dx, plus, and then that same thing is multiplied by that, x du equals 0. I forgot my equal 0 here, but that's beside the point. Okay, now trying to see what they've done here. For the life of me, I can't see how they got to the next step. Okay. Everything I've got in that equation is perfectly fine. Okay. And they suddenly have lost. Okay, let me work through this and see. Okay. This will be x squared plus x squared u squared plus x squared minus x squared u. That's times the dx. Did that help anything? Not particularly. Let's see what we got now. X squared times 1 plus u squared, this is where it's going, plus 1 minus u squared. No, minus u. That's minus u dx is equal to x cubed u minus 1 du. Okay. Now, it's going to be an x squared here. Now let's rearrange this slightly. U squared minus u plus 2 dx is equal to x cubed u minus 1 du over here. Now, will this factor? I hope so. U minus 2 times u plus 1. that doesn't help us any, I can tell. But I guess it really doesn't matter. This is now separable. Okay. So what we'll have here, when you divide both sides by this thing, okay, now they make it seem like something has gone away, and I don't quite see how it has. I think I see my error here. That's it right there. This u dx. I forgot this u. So this will be a u here and a u squared there. Okay, so this does have a u in it here. This has a u squared in it here. Now the x squared u squared minus x squared u squared, they go away. So that leaves us with, let me erase some stuff here. Okay, in fact, let me erase most of this. Start back over again. What I did was correct, but I was using the wrong information. Okay, so what we have here is x squared times 1 plus u on this side, and we have x cubed. Okay, so this just gets down to this. Okay, this is looking more like what they have. Okay, in fact, I didn't need that second line because everything worked out really nicely before. I need all the space I can get, so I'm going to erase this one. Okay, let's make sure I did it right now. Okay, now let's divide both sides by 1 plus u. I'm going to write it as u plus 1, and divide both sides by x cubed. Okay, I'm going to write this as u plus 1. It doesn't matter which order you write it. These go away, these go away, and this leaves us dx over x, and this leaves us u minus 1 over u plus 1 du. I think that's what they've got. They put it on the other side, okay, but it's okay. Now, we certainly can integrate this. If I can find my pen. Where did you go, pen? There you go. We'll integrate that. That's pretty easy. This one, not so easy. Okay, we'll go on and put the integral sign there, but we're going to have to do some fiddling with that. Okay, this is just going to be natural log of x. Say x and write u. I don't know why. And this is equal to, now, I'm going to split this into two integrals here. The integral of u over u plus 1 dx du minus the integral of 1 over u plus 1 du. Okay? Now, this one requires a division first. U plus 1 into u plus 0. That will go one time. Multiply, you get u plus 1. Subtract, and you get a minus 1. Okay? So this will be a minus 1 over u plus 1. Okay? So this one will then be the integral of 1 du, which is just going to be du, minus the integral of 1 over u plus 1 du minus another one, so that's going to be plus 2 of those, I think. Okay, this you can integrate. Okay, this is just going to be u, and I need more room. Okay, this is going to be u plus 2 times the log of u plus 1. Okay, and you're going to have a plus c out there somewhere. I'll write it down now, but we may change it later. Okay. Okay. What they're going to do now, and I'm running rapidly out of room, so I'm going to start erasing some stuff so I can clear some room here. I don't think we need this anymore. If you're hearing something in the background, that's the Roto-Rooter trying to get our drains unclogged. They're not a bad clog, but they're bad enough to be a pain, and since he was here a couple weeks ago, we're still within sort of warranty type area, so that's why we have him back out. I'm hoping I'm not erasing too much. Okay, I think we're getting close now. I think I've got another phone call coming in. I have no idea who that one is, so I'm going to let that ring. This is hard to get anything done with all these phones. That's why in the classroom, I leave my phone down in my office. Okay, I don't have to hear it buzz, but today it was necessary to hear it buzz so he could come. But now I'm having to listen to everybody else buzz. Okay, now what we're going to do here, I think I'll go and erase this too. This is what we wind up with. Log of x is equal to this mess. Okay, now let's plug in what we've got here. With all the erasing, I hope I haven't erased some stuff I need. So this will be log of absolute value x is equal to, and what is u? U is y over x plus, I'm going to write this slightly differently, the log of u plus 1. Well, actually I wasn't going to write it like that. Sorry. Okay, this is going to be u over y over x here too. Oops. Okay. If I can find where I am now. Yeah. Y over x plus 1 squared. And see, I can lose my absolute value bars because the 2 in front is going to square that. Okay. And then we're going to have a plus c, and as the book did, they're going to make that a plus log c rather than, and we'll see why reason in a minute. Okay, a little bit. All right. Now, if you take a look at this, this could be written as y plus x over x, but then this is the thing squared. You see, this is x over x is 1, so it's y plus x over x squared. Okay. Now, and it's the log of that. Okay. Now, Um, what they're going to do is move all the logs on one side and leave this term by itself. So let's leave this as y over x is equal to the log of absolute value x minus the log of y plus x over x, that's really ugly, squared plus the log of c. Okay, now what that does for us is you can put the c and the x together, because when you add two logs, it's the log of the product. So that can be written as the log of cx over, and subtract as division, the log of this thing, which is x plus y, I'm writing it this way now, over x squared. Okay, now you could actually, let's break this down another way, minus log of y plus x squared, and then make this a plus log of x, because that's minus a minus. Okay, so that makes you 2 log of x's here. So let's write those two here, and I'm going to, okay, I feel like I'm running in circles here, but hopefully I'm not too badly. Yuck. Okay, minus the log of x plus y squared. Okay, and I think this has a c in it, 2c. Okay, and this is equal to y over x. Okay, let's see if we're anywhere close. Y over x plus 2 times, well, they left it in a different form. I think I dropped a minus sign somewhere here. But anyway, this winds up being, I'm sorry, I don't want to prolong it any longer. When you combine the logs together, I took them apart too soon perhaps, you get and exponentiate both sides. What you wind up with is the x plus y squared is equal to cx, that's the c from here, x from there, e to y over x. Okay, now I know I'm skipping a lot of steps now too. Here is your, when you exponentiate this, you wind up with an x, and you exponentiate that, you have an e to the y over x. So bring those together, and that gives you that, and the c is in there too. I may have messed up because they're keeping I don't know, suspicious what they're doing there, but they wind up with this form. Now certainly that is not an explicit form, but is an implicit form. So let's go back to the book and pick up from where they left off before. Okay, I'm going to get rid of this for a moment. I wish I could write on the screen that the book's on, but I can't. That doesn't allow me to do that. It can on PowerPoints, but not here. Okay, so basically, let's go back through this and see if we can follow what's happening here. This is your m of xy, there's your n of xy. Okay, both have degree 2. Every term is degree 2, so you can do the homogeneous part. So if we let y equal ux, and then dy is equal x u dx plus x du, right there. So after substituting, you have this equation: x squared plus, and y squared is u squared x squared, so that's where that came from. And that's your dx, plus x squared plus, and your y is ux here. So this will be x times ux, which is x squared u, or they put ux squared, it doesn't matter. And then this is times u dx plus x du, and that's equal to 0. Now, notice they factor out a x squared, which I had done earlier, then I put back in. I wish I'd left it out. X squared here, x squared here, x squared here, and x squared there. All those are dx terms. Okay. Now the steps they've skipped here are the ones that are really pathetic. Here is a u squared x squared, and here they have a minus u squared x squared. That's the term that goes to 0. So the one that are left is x squared plus, but this u is multiplied, ux squared. So keep the x squared on the outside, x squared times 1 plus u. No. Here's the part that's confusing here. It's a minus here, no, okay, yeah, this one disappeared. This one and that one disappeared, and you're left with a x squared plus x squared u. So that's x squared times 1 plus u dx on this side. On the du part, you have an x cubed times 1 minus u du. Okay, so there we're okay. Now, what they do here is divide both sides here by 1 plus u. I was doing it on the other side, they're doing it here, it doesn't matter which. Okay, and divide this by x cubed, and that's what you get here, 1 minus u over 1 plus u du plus dx over x. Okay, sorry, I tried to advance that way. Okay, now this came up to what we had. They did their division, and we got something that looked very close to this. We had it on the other side, so we had a plus 1 here and a minus 2 there. Okay, but anyway, when you integrate this, you get a minus u, and you integrate this, you get a plus 2 log of 1 plus u, and then here you get a log of x, and here you get a log of a constant. Okay, now where did that come from? Well, you wind up with a constant. When you integrate 0, you get a constant. Antiderivative of 0 is a constant. But rather than write it as a constant, they wrote log c, which we had done too. Okay, well, this u is from up here, u is equal to y over x. So you put the minus y over x here, plus 2 times the log of 1 plus y over x, plus the log of u is equal to log of c. And again, they're making the constant as a log. Yuck. Okay. Now is where they use the property of logarithms. Oh, goodness, there's Ryan. I didn't see him there. Let me get Ryan in here. All right, 4 out of 5. We're only missing Jemanuel. Has anyone known as if Jemanuel's tried to get in while I was out? We don't have Jemanuel. Okay, good to have you though, Ryan. Where we are is Chapter 2, First Order Differential Equations. We're in Section 2.5 on page 73, solving Example 1. Okay, we're right at the end of Example 1 here. Okay, let me scoot back up just a tad. Whoa, goodness gracious, that was too much of a tad. I forget I can't use the scroll on the right hand side. It's going to take me a while to get there. Okay. All right, here we go. Example 1. Okay. Right. Here's where we got to. Okay. Now, using the properties of logarithms, what that means is you can put this as a square here. Now, they skipped a bunch of steps here. They, like I did this over, that be x plus y over x. Okay. Then they squared that, and that gave us x plus y squared over, and it should have had an x squared in it here. Whoops, here's Jemanuel. We got perfect attendance today, folks. Way to go. Okay, we got everybody here now. Okay, now here's the part, okay, that is not quite so obvious. You pull this up here, and that gives you log of x plus y over x, but the whole thing is squared because you move the 2 over here. Okay, but you could have written that as log of x plus y squared minus log of x squared, which is log of 2x, and that gave you then a minus 2 log x plus log x, so that's a minus log of x. That's the part that they just sort of gloss all over here. Okay, now then you move that back in the denominator here because it's a minus, and they combine that with the minus from here, so they put the cx together here. This would be when you subtract the log of x squared here, which is log of minus log of 2x plus log of x, that would give you a minus log of x. Okay, then do a minus log of c, so that's minus a log of cx. So that's in the denominator. It skips so many steps here. That's equal to this. Now you exponentiate both sides, and that gives you log of exponential of a log just gives you this argument here, and you got e to the y over x. But when you exponentiate this, then you have x plus y squared on the left hand side. then multiply the right hand side by cx, that gives you that, then e to the y over x. They sure skipped so many steps in doing that, but that's what they did, okay? And that's one way to solve a homogeneous differential equation. Now, here's a phone ringing again. I think this is the same guy, so hold on just a minute. Good afternoon, Charles Fowler speaking. Yeah. Okay, let me get off the phone. I'll be right with you. Okay, I'm going to have to pause the recording for just a minute. We got a plumber here. It says, although either of the indicated substitutions can be used for every homogeneous differential equation, in practice, we try x equal vy when the function m of xy is simpler than n of xy. See up here, the one we just did, and I can't move that. I got to move James out of the way here a moment. Okay. Whoops. Going the wrong direction. Nope, I was going the right direction. Here, they're equivalent. It doesn't matter which one you use. But if the m of xy, this one on this side, is a lot simpler than that one, then do the other substitution, x is equal to vy, okay? And then that will that will just, it makes life a little easier, okay? So just remember that, and as it turned out with all these interruptions, we basically just got to Bernoulli's equation. So we got through the homogeneous equation, but that's all. Sorry about that. We'll start next time with Bernoulli's equation. Were there any questions? Okay, basically we didn't get much covered today because of my problems with the plumber and other things, but that's taken care of hopefully for good now. Homework exercises here. You can do any of the odds 1 through 9 on page 75 that are any of those in the back of the book. Do either 11 or 13 if they're in the back of the book, and stop there because the next is a Bernoulli equation and we haven't done those yet. Okay, so as soon as we finish Bernoulli, then we'll be able to move on. Okay, those first group 1 through 9 I think are all homogeneous. Okay, 11 through 14 are homogeneous with initial value problem. Now we didn't do one like that, but you've done initial value problems before. So we'll pick up with Bernoulli next time and hopefully finish that and move on to 2.6, which is the numerical method. Any questions? Sorry about all the interruptions today. Any questions? All right, I'm afraid I put you all to sleep. I'm going to stop the sharing for right now. All of you hung with me. Thank you so much. And if you're still there, at least your names are still there. And I'll go on, if you don't have any questions, end the recording, and I'll see 3 of you tomorrow, okay? And then I'll see you all on Wednesday. Some of you twice. Okay, thanks much. We'll see you next time. Bye-bye.